Okay, I want to talk about slope graphs. So here's a graph. I don't have a scale on it. Well, in order to do a slope graph, you kind of need a scale. So I can put a scale on this graph, maybe appropriate to a situation. Let's just say that this is 160 and this is 80. I choose these numbers because they're easy to subdivide a number of times. Okay, so I can subdivide the 160 and get 80. I can subdivide the 80 and get 40. Cut this interval in half, I get 120. And then I can cut each of these in half and each of these to get quarters. And each quarter is going to correspond to 10, obviously. And there's nothing new in what I'm doing here. So I cut the 80 in half, I get 40. Cut the 40 in half, I get 20. And I cut the 20 in half, I get 10. And I could label a 10 on this graph. There's a 10. So we see that we have units of 10 if we do the small tick marks. Okay, and then I can have 30 here. I can subdivide this. It gets 60. Subdivide here, I get 70. Subdivide here, I get 50. And this is something you should be able to do very quickly. Just because if you do it quickly, it means you probably more or less understand it. And I think you do, but it's also handy because when you're doing a graph, it's good to be able to just slop something down in just a minute or two so that you can work on it. And hopefully something with a little bit of accuracy. Okay, so now I don't know what this is. It could be the flow diagram, or the graph of the depth versus time for the flow. It could be the frequency versus time for a pendulum. It could be anything else, just some graph that's concave upward but decreasing. Okay, now I want to define a slope graph. So let's just say you have 3 points on this graph. Here, let's make it 4 points. Here, here, and here. Okay, well, coordinates to this point looks like it's about 50, 75. So I want to label that. Going to have to be kind of small to get it in here. I don't want to label it on the other side because ultimately I'm going to do just what you probably would anticipate I'm going to do. I'm going to construct fundamental triangles, 3 fundamental triangles. Okay. So at this point, I'll go ahead and label it up here, 50, 75. This point appears to be about 73, 57. So I'll label that on this side to leave myself room to label the fundamental triangle over here. Okay, then here we get, I don't know, pretty close to 110. That seems to be pretty close to 40. Nice round numbers. And here we have about 155. Come over to here, 33, let's say. Now we can go ahead and do the rise and the run. The run from 50 to 73 is 23. The rise from 75 to 57 is negative 18. Of course, now I'm going to want to label the slope over here where I've labeled this stuff, but I'll put that in a minute. Okay, the rise from here to here, or the run from here to here, is going to be 37. And the rise is going to be negative 17. The run here is going to be 110 to 155, that's 45. And the rise is negative 7. So we get slopes. We can easily calculate the slopes. Now I'm going to do calculations quickly in my head, and I'm going to do decimal equivalents. The slope is, of course, negative 18 over 23. Now 18 over 24 would be 3/4. So that's going to be about 4% more than 3/4. about 0.78 or 79. So I'm going to go with 0.79, and it's negative 0.79. Negative 17 over 37. 17 over 34 is half. 4 is about 10 or 12% of 37. And so we add 4% of a half to a half, we get negative 0.52, and I hope I did that right. So I'm going to actually draw these hypotenuses, hypotenusi, I don't know, hypotenuses. And I'm going to say that's negative point. Actually, if I do a long division, I find that that's negative point, well, just what I said, 0.52. Excuse me. And this is negative 7 over 45. Well, negative 7 over 6, that would go into 42 6 times, go into 49 7 times. So it's going to go into it about 6.5 times. Went into it 6 times, it'd be 0.16, be 0.14. So I'm going to say it's between, probably around negative 0.15. So there are my 3 slopes. Now, those are all simple calculations. You might not be able to do them in your head, and you might be able to do them in your head and even more accurately than I can, but that's okay. So now we have the information that, where to put my white chalk? Okay, interval for each slope. Okay, the interval here would be, now I got to go back to my estimates. No, I can read it. I know where to look. It's 50, 73, and the slope which I'll also refer to as average rate of change, abbreviated ROC, is negative 0.79. Okay? Next interval is 73 to 110. And we have negative 0.52. And then we have the interval 110, 155, and a slope of negative 0.15, approximately. Okay, well, I'm going to give myself a little room here. That word is midpoint. Now what I want to do is I want to draw a graph that shows average slope versus the midpoint of the interval. Okay, well the average slope, the midpoint between 50 and 73, two ways to do it. The difference is 23, half of that's 11.5, so the midpoint would be 61.5. Alternatively, add 50 and 73, you get 123, divide that by 2, again you get 61.5. Okay? Now if I add 73 and 110 to illustrate that, I get 183, and half of that is 91.5. And then, yeah, that's right. Confused myself. 110 and 155. Difference is 45. Half of 45 is 22.5. 110 and 22.5 is 132.5. And I'm using decimals because it's natural when you're locating things on a graph if you're not constructing the points, and that's something I'd like to have time to actually talk about, but I don't think we're going to have time in this course. But anyhow, 132.5 should be halfway between 110 and 155, just to check myself, because we always want to check when we can find the time, and even if we can't find the time, we want to check fairly often. So 61.5 would be, okay, well, let's look at this. First interval would be here. Second interval would be from here to here. Third interval would be from here to here. The intervals between these points, or at least the coordinate of these points on the x-axis. The intervals between the point directly below this and the point directly below this, and so forth. Okay, halfway would be 61. There's 40. There's 40. There's 50. There's 60. There's 61. I'm going to put a little X in the midpoint. It looks like it's about halfway. I got the graph scaled halfway decently. So, you know, if it looks good, and if I think my calculation was correct, then I'm in pretty good shape. Okay, then between here and here, the midpoint's supposed to be 91.5. Here's 80, here's 90, and 1.5 would just be slightly to the right of 90. That looks like it's pretty well in the middle of this interval. So again, there's some confirmation, at least a plausibility check. So if I was off by 10, it would be very clear that I'm not in the middle, right? That's very easy to be off by 10 or even 5. Okay, so 132.5, here's 120, here's 130, and there's 2.5. Looks a little bit closer to this end of the interval than it does to that one. Didn't do that on purpose. Well, let's see. I add 22.5 to 110, I get 132.5. I add 22.5 to that, and I do get 155. So if there's any distortion here, it's just because of the way the graph is drawn. Maybe I put this bracket a little too far to the right, or something of that nature. So there we have it. There's a picture. Now we take these points on the interval and we put them over here, the midpoints on the intervals. We could even put the intervals over here. It'd be good information. So let's just do my 160, my 80, my 120, my 40, and then roughly locate my 10s. There they are. Now what kind of scale do I want to use for the slope? Well, the slopes go up to negative 0.79. Now, actually, I don't want to graph negative slopes, although I could. And they would be down here. And you'd have negative 0.79 be further down than negative 15. It's a little inconvenient. And really what I'm after is the steepness of the graph for reasons that you'll see before too long. So I'm going to put absolute value signs around this. The magnitude of the average slope. Okay, so this isn't officially the slope graph. The slope graph is actually going to be flipped downward on the other side of the x-axis, but the magnitude of the average slope is going to be up here. Now, the magnitudes of these numbers go up to 0.79. Well, conveniently, and I didn't set it up this way, I just slopped down a graph and, you know, made up a scale, but it's fairly nice. The slopes go up to 0.8. Now I'm about 0.8. Okay, so I'm not going to go all the way up here because I might want to extend the graph higher than that for some reason. So there's 0.4, 0.2, 0.1, 0.3, 0.6, 0.5, 0.7. And now the point 61.5, negative 7.79 goes on this graph because we have midpoint down here and we have average magnitude of the average slope up here. So 61.5, and I'm going to go ahead and sketch in my intervals again. So I've got 50, 73. Then I've got 73 to 110. and then 110 to 155. With midpoints here, here, and at 132. Okay, actually looks a little better in this graph. I don't know why. Okay, well, you know, these markings help me identify the intervals on which I took the midpoint, and that could be important information relevant to the accuracy of the model we're going to get from this graph. And now I go ahead and plot my slopes, and I'll use the orange mark, chalk, to be consistent with this. But my slope, magnitude of the average slope on this interval, got to do something about that, is 0.79. I'm probably blocking the board, but I want to do this with some accuracy. Okay, so there is this point, midpoint, well, slope, magnitude of the average slope versus midpoint. Then it's going to be 0.52 here and 91.5 here. 0.52, there's 0.5, so 0.52 going to be along this line. I go directly up from here, I get a point. And then negative point, well, magnitude is going to be 0.15 at 132.5. Well, 0.15 is here. And there we have it. Those 3 points are on my slope graph. Now 3 points is a sufficient number to attempt one of two things. Okay? From this point to this point, if I did a straight line with these 2 points, it would go significantly higher than this point. If I did a straight line between the first and last points, it would be significantly lower than the middle point. That could happen in one of 2 ways. Okay? One way is my estimates of these coordinates are pretty uncertain. You know, they're not too far off. I'm not off by 10 anywhere. Probably not off by 5 anywhere, but I could be off by 2 or 3 on any of these coordinates. And you could calculate how much influence that would have on my calculation of the slope. If I'm a little bit low on calculating my run and a little high on calculating my rise, then I get a bigger error, or you know, unavoidable uncertainty. There's a difference between error and unavoidable uncertainty. But I get a bigger uncertainty, and on a hand-drawn graph, the uncertainties are pretty big. So it's entirely plausible that the best thing I can do with this data is model it with the best straight line I can use. Okay, now, the best straight line is not the straight line through the first and last point. It's not the straight line through the first and second point. It's not the straight line through the second and the last point. It's a straight line that, in a sense, comes as close as possible on the average to these points. Now, I'll qualify that. Really, you want to minimize the sum of the squares of the distances from the points. We're not going to split hairs on that. So to draw to draw a straight line that best fits these points, we're just going to try to get as close on the average as possible to the points. And that's probably going to give us a line, oh, I don't know, let's see. So I'm going to say, well, I'm just going to slop one down here. Okay, now the line cannot be expected to go through any of the points. You don't want to try to make the line go through any of the points, because almost always, by adjusting the line a little bit, you can get closer to the other points on the average. Now this line looks like it goes right through that X, but it doesn't really go through the center of the X. It's just where it happened to fall. And you can actually estimate how much higher this is, how much lower this is. If this is 0.1, then 0.01 would be a tenth of that distance. That looks like it's off by about 0.03. This one looks like it's off by about 0.01, and this looks like it's off by about 0.04. So if it's that, it totals up to 0.08. On the average, we're off by about 0.03, 0.027, 0.03. Can I adjust it to make it a little closer in the average? And then they have the question, well, could I adjust it so the squares are a little closer to the average? And as I say, I love to discuss that. I might do a video on it. I don't have to let it go for right now. Anyhow, you get a line that best fits the points, and that's pretty close to what you call the regression line. You might have learned to do a regression line on a calculator. You might well have learned how to do the regression line on a calculator with no idea how to sketch one. Well, I think you need to be able to sketch it before you do it on a calculator. I think you have to know what it means before you start calculating with it. The curriculum, I think, doesn't do enough of building the conceptual idea. Although if you learn how to do it on a calculator and then use that to develop the conceptual idea and still develop the ability to actually draw one of these things that's fairly close, there's an argument for that approach also. And I don't take any real position which argument's the better, but I think you need to do both, and I'm pretty strong on that argument. Okay, so there we have it. Okay, there's a straight line graph that does a pretty good job of fitting these points. Now there's another alternative. So we can have a straight line model. But if you think your estimates here are really accurate, and you think there isn't so much uncertainty in this that you can't take the idea that the slope from here to here and the slope from here to here being different really indicates that this graph has a downward curvature. Okay, so I could then say, okay, well, no, actually I think it's not really a straight line. I think we've got some curvature here, and the graph should look like this. Okay, so this is a graph that acknowledges the curvature. Now there is another graph that's going to look a whole lot like this one, but maybe not quite exactly the same. Maybe there is, well, okay, I'm going to call this red thing the quadratic graph through 3 points. Okay? And that is a graph of a quadratic function I'll use t for my variable instead of x, with the idea that maybe this somehow represents something that's a function of time, in the same sense that the flow is a function of time. Now what we're probably going to find is that your graph of the flow data, the depth versus time graph, is itself quadratic, which makes this graph linear. And that's going to be an assignment that I ask you to complete. So anyhow, quadratic function has this form. It has three parameters, A, B, and C. If you know the numbers A, B, and C, then you know what the model is. You know what the function is. Okay, well, I'm not going to go into that now. I'll go into that in a separate video, but there's some main ideas. There's the idea of a graph. There's the idea of a slope graph. And these graphs are both very important. There's another graph that can be very important in some situations that I think we'll have time to talk about, but not today. Okay, so there we have it. There's a graph of something. There's your slope graph. Between the quadratic graph and the flow data graph and your pendulum data graph, both of which have pretty accurate observations, you're going to find that one is clearly, the slope graph is going to pretty clearly be a straight line, and that's going to give you some important information that's connected by geometry to the geometry of the bottle and the tube. And another one is going to clearly be curved, and is going to give you a composite of two basic functions. Okay, we're going to have to talk a little bit about inverse functions to get that idea, so I'll go on with that in another video.